So in today's module we are going to look into one of the most important method, and for the good reason the method is also called as mother of all methods. We have discussed some of the theoretical background related to method of moments while we discussed the variational method and also finite element methods. That being said, we are quite prepared to look into the basic idea behind method of moments at large. We will start looking into some of the motivation behind it, historical aspect as well, and take you through some examples. So in today's module we will start with the background. As usual, we will look into the theoretical aspect of the method of moments, and we will look into some of the applications. With that, let us start with the background itself. So the method of moments actually started in 1965 by G.H. Richmond, who actually introduced this method to engineering electromagnetics community at large, mainly for scattering problems. That being said, the problems what he approached is mainly looking at scattering applications, and later on, couple of years later, it was actually Harrington who introduced the method to wider applications like antennas and various applications in engineering, and he popularized the method further, introduced various mathematical aspects using simple examples. So his publications, both the books and also the transaction papers which he introduced, method of moments, are even today one of the most important references for method of moments. That being said, there is a similarity to the Galerkin method or the finite element approach which we discussed. For example, we will see here in the Galerkin method we are basically going from a linear partial differential equation to a matrix equation. In the case of method of moments, we are going to start with the integral equation, not the partial differential equation like in the case of Galerkin method. So we are going to start with the integral equation, and we are going to use certain PEC approximation on the boundary conditions, perfect electric conductor approximation, and also the entire approach is based on currents. So what we in essence get is similar set of matrix equation, but in the case of the method of moments what you get is basically the impedance matrix and the current vector and the voltage vector. This is basically a kind of a Ohm's law where you have the R represented by the matrix here, the I represented by the vector here, and voltage represented by the vector on the right hand side. So in a sense it is a very similar approach to the Galerkin method, but the theory is a little bit different. So we will start with the theoretical concept itself. As usual, we will start with the time domain Maxwell equation represented by curl of E and H field, and similarly we should also have the divergence condition. If we cannot define the divergence condition, it is difficult to uniquely compute E and H. So both the curl formation and the divergence equations are important for us to uniquely compute, in addition to the boundary conditions as well. So we are not discussing here the boundary conditions. So this is the time domain Maxwell equation, and when we go into the frequency domain we can substitute for the time derivative minus j omega. Please be aware that some literatures use j omega. If you use the convention of j omega instead of minus j omega, your signs here has to change accordingly, but the general formulation is pretty straightforward. So when you go for the frequency domain formulation, so the minus j omega is getting substituted for dt, and the equations are getting transformed accordingly, and the divergence equation remains the same. When we can substitute the constitutive relationships, basically the constitutive relationships are the relationships between D and E and B and H. So when we substitute them, the divergence conditions become like this. What we essentially have is divergence of mu of H is equal to 0. So we take that one and we say when the divergence of something is 0, that means that something is actually a curl of some other thing. So that is a basic mathematical identity. So when we say the divergence of mu of H is equal to 0, what we are going to say is, we are going to say this mu of H is actually a curl of some other variable, and that other variable we call it as A, which is a vector, and this is nothing but the magnetic vector potential. Remember, the counterpart of it in the case of electric will be the electric scalar potential. As compared to the electric scalar potential, which is very much a physical quantity which you can basically measure in laboratory experiments, magnetic vector potential is a purely a mathematical construct. It is a purely mathematical construct in the sense there is no physical counterpart for it. So we do that mainly to do the analysis simple. So the magnetic scalar potential, there is no physical counterpart to it. So we will start with substituting this A into the first curl equation what we had. So what we had is, we had a curl equation that says the curl of E is going to be given by J omega mu H. So what I am going to do here is, I am going to take J omega mu outside, and for H I am going to substitute curl of A divided by mu. So once I do this, what I am going to do is I am going to bring them to the left hand side. So curl of E minus J omega curl of A equal to 0. So once I have this, as you can see in the slide, I am going to write this equation as curl of E minus J omega A equal to 0. So now we are going to look into another vector identity. When the curl of something is equal to 0, that means the something is going to be a gradient of something. So in this case we take gradient of phi, which is the electric scalar potential, and by convention we use a minus sign. So this particular thing will be equal to this. So what we have got now is E minus J omega A is equal to minus the gradient of electric scalar potential. So what we can write them, we can also write it in the time domain form, which will be useful for us. So now what we will do is, we need to find a way to solve the problem of addressing more variables than the degrees of freedom. So somehow the mathematicians use this term called gauging, and this particular gauging is referred to Lorentz gauging, named after the great Dutch physicist called Ludwig Lorentz. And the reason for doing that is to cope up with the degrees of freedom of the variable itself. We are not going to go into the mathematics of it, but we will see how did we come to that Lorentz gauge here. So what we have here is, we will start with the basic Maxwell equation. The curl of H is equal to minus J omega epsilon E plus J. So when we multiply mu towards this entire equation, so what we will get is but we know for this one mu of H is the curl of A. So curl of curl of A is equal to minus j omega epsilon mu E plus mu j. So with this we are going to manipulate the equations further. So we will, what we have got now is curl of A is equal to minus j omega epsilon mu E plus mu j. What we will do is we will substitute the value for E in this equation. We can transform this entire thing in the time domain. So what we will get is curl of A is equal to minus j omega will be dt. So we will get mu epsilon dt E plus mu j, and we know E equal to minus and we will have the value of minus dt A, this we know. We can substitute this value for this E here. So what we will get is curl of A is equal to mu j plus epsilon mu dt minus gradient of phi dt of A. This left hand side is has a vector identity which is nothing but gradient of the divergence of A minus the Laplacian of A is equal to mu j plus epsilon mu dt of this particular variable here. So I can expand this inside term as follows. What I will get is mu of j minus epsilon mu, the gradient of the time derivative of phi minus epsilon mu dt square of A. So you can notice we have two terms. We have one term, the gradient of the divergence of A on the left hand side, and we have the gradient of the time derivative on the right hand side. So we are going to bring them one side and then rearrange the equation as follows. So what we have now is the gradient term, divergence of A on one side plus epsilon mu dt by d, the time derivative on the electric scalar potential, and the right hand term which is mu j minus epsilon mu d square t A, and then the Laplacian term from the right hand side which is plus Laplacian of A. So what you see here is the condition that will lead us to the Lorentz gauge. The Lorentz gauge is nothing but this term we are setting it to 0. So the divergence of A plus epsilon mu dt of phi is set to 0. So this is the Lorentz gauge, and that is what you will see in the equations to come. So when this is 0, so gradient of something is 0, so and essentially you can equate this to 0 and then you can compute the values accordingly, and you are coping up with certain degrees of freedom issues. So the idea behind the Lorentz gauge is exactly that. So what we have done now is the derivation for the Lorentz gauge. So you can rearrange this term accordingly. What you will get is divergence of A is equal to minus epsilon mu dt phi, and then you can substitute for dt as minus j omega, and then minus minus get cancelled, you will get j omega epsilon mu phi is the divergence of A. The reason for doing this is also due to the Lorentz Helmholtz theorem. Helmholtz theorem says that it is not enough to talk about only the curl of defining the curl of A, we need to also define the divergence of A to uniquely find the value of A. So we have defined curl of A as mu h, and now we have defined the divergence of A as j omega epsilon mu. So this is in fact the necessity for us to mathematically compute the value of mu of A. So the background behind Lorentz gauge is something important, and that is what we have tried to explain you now. So let us go into the method itself. With the Lorentz gauge, we are going to substitute the value of A into the curl equation. So what we have got is the curl of A divided by mu is equal to minus j omega epsilon E plus j, and for a homogeneous equation what we have got is putting E equal to j omega minus the gradient of phi, you will get the value accordingly. So what I am going to do is I am going to substitute the value for E here and get an expression for the curl of A. This is curl of A. I am expanding curl of A using the vector identity, which is the gradient of divergence of A minus the Laplacian of A is equal to minus j omega mu epsilon multiplied by j omega A minus gradient of phi, which is the value of E, plus mu j. So rearranging the terms, what I have got is an expression for the Laplacian of A plus omega square mu epsilon A minus, I am taking out the gradient term outside like I did before, that is equal to minus mu j. So we have the Lorentz gauge here. So essentially what I am going to do is I am going to substitute the value for this Lorentz gauge, and when I substitute this particular term will disappear because we will get a value minus j omega mu epsilon phi plus j omega mu epsilon phi. So this term will disappear. What I will get is an Laplacian of A plus omega square mu epsilon A is equal to minus mu j, and that is what I have written here. And this is a wave equation using potentials. So what I have used here is directly the magnetic vector potential, and you can substitute the value omega square mu epsilon is equal to beta square. Once you do that, what you get is the same equation written in terms of beta, and this is the vector wave equation that relates magnetic vector potential to the current. You have seen a similar equation related to the electric scalar potential, but this is the magnetic scalar potential counterpart, and in matrix form when A is a vector with Ax, Ay and Az as its component, similarly J is a vector using Jx, Jy and Jz as its component, we can write this in the matrix form. For a simple case where we have a Z oriented antenna, where the antenna is approximated as a thin wire, you can assume that the current density is only Jz and Jx and Jy are 0. What you will get is an expression for the thin wire antenna as follows. This expression essentially demands our Ax and Ay to become 0, and using the Lorentz gauge what we get is basically the formulation that can be written of this form, and the electric scalar potential reduces to Ez minus j omega Az equal to minus d phi by dz. There is only variation in the z direction, and combining both this equation and this equation you essentially get the expression for Ez using only the magnetic vector potential, and that is the reason why we started with the magnetic vector potential. You wanted to compute the value of the electric field as a function of the magnetic vector potential, and the idea now is, suppose that you have a simple antenna which is a very thin wire antenna, and I am going to zoom it to show its cross section. The cross section here is, let us say, 2a, and this 2a is very small compared to the wavelength. So 2a is very small compared to the wavelength. And now suppose that this antenna is oriented in the z axis, so this is the z direction. We can assume this antenna is decomposed into many small identical elements. So let us say we are splitting it into small elements, and inside these elements there are individual sources that we are going to talk about. So what we are interested is we are going to find the value of a field at a point, let us say r, due to the location of some charges at r prime. So in other words, what we are looking at is the response of certain field due to the source at certain location is represented using a function called as the Green's function. So Green's function is nothing but a response function which we are going to compute due to certain source at certain location, and assuming that the distance, the vector r, magnitude is given by r prime minus r, and we are going to compute the value of the field at this observation point. So this is the observation point, and this is the source location. So what we are going to do now is basically compute the value of the field at this point due to this one. Essentially this is the idea behind the Green's function, and what we will do is the overall solution due to this entire antenna is going to be the superposition of this individual elements. So what I will do is basically compute at this point due to the superposition of all these points. So you get the idea. So we will use this principle to compute the value of the response, the overall response, and the individual response of the tiny elements are the Green's function, and the overall solution is going to be the integration of the Green's function itself. So at this point we will stop, and in the next module we will come and compute the value of the Green's function for this test case and take it from there on. Until then, goodbye.